In this video, we are going to talk about some basic properties and constructions of prevarieties. So before, what we have seen is that we can glue affine varieties together to form prevarieties. And now we really need to develop all the language that we're used to for these prevarieties, because there's lots of notions, open, closed subsets, dimension, and so on, that we talk about that we talked about in the context of affine varieties. Now we want to see in this new language of prevarieties which of those make sense. And it turns out that most of them still make sense. So as for topological properties, well, any prevariety by definition is a ringed space with extra properties. So in particular, it's also a topological space. And this means that things like open and closed subsets, connectedness, irreducibility, and dimension, all of these we have treated in the context of arbitrary topological spaces. So all of these still make sense. So now I can, from now on, just say X is a prevariety, it's dimension 3, and you just know what it means because we have discussed it for arbitrary topological spaces. Moreover, by definition, X has a finite cover by affine varieties. And affine varieties, in particular, are Noetherian topological spaces, in the sense we discussed before. And then there was an exercise in Gutmann's script, which said that if you have a topological space with a finite cover of Noetherian spaces, then also X is Noetherian. And so any prevariety is Noetherian, and therefore, as we have seen, it also has an irreducible decomposition. So it now also makes sense to speak of the irreducible components of prevarieties. So this was the purely topological stuff. And now we also want to see what are the analogs of things like being, for example, an affine subvariety. We know what that means. So what does it mean to be a sub-prevariety in the same sense? So here's the construction. X is an ambient prevariety. For any open set in X, U, the claim is U with its restricted structure of ringed space is again a prevariety. And indeed, well, we have by definition X having a cover by Xi affine varieties, and then intersecting everything with U, U has a cover by these spaces Xi intersected U. And we'll see them now as open subsets of the affine variety Xi. And then we know that the distinguished open subsets form a basis. So each of these has now a cover by distinguished open subsets, but these are affine varieties themselves, as we have seen. So we have here a finite union and then again a finite cover here. So overall U is still covered by finitely many affine varieties. And so it satisfies the definition of prevariety. And this U with this restricted structure, we call it an open sub-prevariety of X. And then there's also an interesting morphism. You can just take the inclusion of U inside X, and then by basically general nonsense, this will be indeed a morphism of prevarieties. And we call morphisms of this form open embeddings. Okay, this was the case of open sets, and the case of closed sets is also very important, but slightly more tricky, as we're going to see. So suppose that Y inside X is now a closed subset. The question is, how do we define OY of U when U inside Y is open? So we want to define the structure of a ringed space, making this into a prevariety. And the problem, in contrast to what we did before, we cannot just take this here because U might not be closed inside, might not be open inside the ambient space X. For example, if you have such a one-dimensional thing, like an open set would just be some open part of this curve, but this will not in the ambient space be an open set. So we need some new idea. And that idea is that we define these regular functions on U as functions from U to K, which are at least locally restrictions of regular functions on X. So the idea is define for U inside Y open the ring of regular functions as these maps here, such that for all A inside Y, there exists an open neighborhood V of A in X. And the psi, this will be a regular function on V, such that the function phi defined in the neighborhood of A inside U here is a restriction of the function psi on V. Okay, and you can write this down, and then you can go through all of the necessary checks. So these things are closed under addition and multiplication with element in K. So this is indeed a K algebra. And then the claim is this gives a sheaf of K algebras. So certainly if you restrict such a thing to a smaller open set, you still get something of this form. So it is a pre-sheaf. And then the sheaf axiom, the remaining thing to check is that this kind of existence condition, which says that basically if you have things defined on the cover, then they patch together, or in other words, you can check this condition on an open cover. And this is true because the condition phi is on phi is local. That's why we always say there are locally restrictions of regular functions to make this sheaf axiom work. And then, well, we have constructed this sheaf of K algebras. So Y together with this sheaf is a ringed space. So that's already good, but we wanted more. We wanted it to be a pre-variety. So we need to show that this has a cover by affine varieties. And of course, what we want to use is that X has a cover by affine varieties. But there's one kind of crucial compatibility check that we need to do, namely, if you have W inside X in the big space, an affine open set, then there's kind of, then you can look at W intersected with Y. This is a topological space, it's an open subset of Y. And there's two ways to put a sheaf of K algebras on this. The first is we have just constructed OY, and then of course we can restrict it to this open subset here. So this is one sheaf of K algebras. The other one, this is a bit more subtle, so somehow W itself has, of course, a sheaf of K algebras, its structure sheaf. And then you can also see W intersected Y now as a closed subset of W. And if you have an affine variety in a closed subset, we also, well, then it is an affine subvariety. And so we do have another sheaf of rings on there, which is just a structure sheaf of this affine variety. And so this thing here carries a second structure sheaf like this. And well, then the hope is there's a compatibility which would mean that this structure sheaf and this structure sheaf agree. And you can formulate this as saying that the identity map from here to here is an isomorphism of ringed spaces. And this is an exercise that you can do. And it's kind of important to see that this construction of this ringed space really makes sense and is compatible. Okay. And once we assume this exercise, well, then we can finish our construction by concluding that this thing here, Y and OY, has a finite cover by affine varieties. Because indeed, if you have finitely many affine opens W covering X, then the W intersected Y cover Y. And we see that this open cover, this is isomorphic to this thing here, which is an affine variety with its structure sheaf. And so W intersected Y has a cover by F1 varieties, so it is a pre-variety. So we have finished the construction. We constructed this pre-variety, and such a pre-variety Y we call a closed sub-pre-variety of X. Now, both for open subsets of X and for closed subsets of X, we have given them the structure of a pre-variety. One remark is, now you could hope, well, if it works for both open and closed subsets, then probably it works for all subsets. But that's not the case. So for general subsets, we cannot give it a good structure of a pre-variety, even if they're, I mean, not super terrible, but for example, here in A2, we can take a subset Z, which is a union of an open and a closed subset. So we take A1 cross A1 minus 0. So this is almost all of A2 except when one of the coordinates is 0. And we take the union with a closed point, just the origin. And that's a kind of weird mixture. And the claim here is that this is not naturally a pre-variety. So for example, if you wanted to show this, you would look around this point, and then you would have to argue that around this point, it doesn't look like an F1 variety. I don't want to go into the details, but it's kind of fact that this doesn't make sense as a pre-variety. So we can't put it on arbitrary subsets. And in a certain sense, this shows that it's a bit dangerous to mix open and closed subsets, at least taking the union of those. But what you can do is you can take the intersections of open and closed subsets. And these are what is called locally closed sets. And there's a kind of optional video, if you're interested, which discusses a bit locally closed and constructible sets. And this shows some really nice results, but they're not really needed for the rest of the course. So feel free to skip it, but I think it's an interesting small digression. Okay. And then, well, we did define open and closed sub-pre-varieties, and there's a nice exercise. So about the properties of closed sub-pre-varieties, because now there's a lot of compatibility checks which we can do. So for example, if Y inside X is a closed sub-pre-variety, then you can again write down this inclusion from Y to X. And the claim is this is again a morphism. And morphisms of this form are called closed embeddings, in contrast to the open embeddings that we had before. And the second thing is that that is really one of these compatibility conditions, that if you have a map from F from Z to X, morphism from a pre-variety, which happens to land inside a Y, this given closed sub-pre-variety, then of course it makes sense to write it as a map from Z to Y, Z theoretically. And the claim is this is then again a morphism. So somehow if you factor through a closed sub-pre-variety, then also the map to that as a pre-variety is a morphism of pre-varieties. So these are kind of subtle things, but because we did all of these constructions of these sheaves by hand, we then need to check afterwards that everything works nicely together. And that's part of this exercise, and that is a kind of good way to recall the definition that we gave of these structure sheaves. And then a remark here is that so we have seen open and closed subsets, and then we can also look, if we're given a morphism of pre-varieties, what about the images and the inverse images? And so in that situation, F from X to Y, the claim is that the image of an open or closed sub-pre-variety is not necessarily open-closed inside Y. And there's a concrete example here. You can look at the map F from A2 to A2, which sends xy to x times y, comma y. That looks pretty harmless. But then if you look at the image, the claim is if you take the full image of all of A2, then it's exactly this kind of strange set Z that we saw before. which is neither open nor closed. So that was given by this union here. And so you see here, we started with something, A2 inside A2 is actually both open and closed. But the image here is neither open nor closed. So somehow none of the four possible properties would hold. And for proving that, I mean, if you want, you can also skip that and prove it for yourself. But I mean, it's not super hard. So A2 has a big open part, which is A1 cross A1 minus 0. And the claim is F restricted to this open part U is actually an isomorphism from U to U. Because, well, if you restrict the second coordinate Y to be non-zero, then you can reverse this map. Because you send U comma V to U divided by V comma V. You can just check this is the inverse map. And so certainly this part here is contained in the image, but then the rest, somehow A2 minus U, this is just the set where the second coordinate is 0. And well, if Y is 0, then this is always the point 0, 0. So this kind of contracts this line here just to the point 0, 0. And so the image is given by the union of U and this single point. So there we see the image is not really nice in the sense that it's open or closed, but it is true. I mean, this here is the union of something open and something closed. So it's not a super terrible set. And in this digression, you see a result which characterizes what are the images of morphisms like this. And these turn out to be these so-called constructible sets. But anyway, so somehow the images are not necessarily against subprevarieties, but at least the final thing to discuss is that, well, since F is continuous, of course, the preimage of an open or closed subset is open or closed. And so the preimage of such a subprevariety is also a subprevariety of the corresponding form. So these were some of the properties of prevarieties that generalize properties of the affine varieties that we have seen before.